Today we're going to go over the theorem, which shows that if a limit exists, then it must be unique. This is a key theorem in real analysis and complex analysis as well. So the first step we're going to do is we assume that the limit exists, right? So because the limit exists, we can assume that the limit of a of n is equal to x, and the limit of a of n is equal to y, where x comma y are elements of the real numbers or complex numbers, depending on what your sequence is. This is specifically for the real analysis proof, but if you're doing the complex analysis version of this proof, you just assume they exist in the complex plane. So this shows that the limit exists. In order to show our uniqueness, all we have to do is we have to show, or to show uniqueness, we must show a is equal to b. So we're given this like limit of a n equals x, but we can't do much with it, right? It's a bit generic. So we want to get expand it to its proper real analysis definition. So that's going to be for all positive distances, which we'll call epsilon of x, and we'll reserve positive distance by making sure that our epsilon of x is bigger than 0. There exists an n in the element of natural numbers such that if our sequence is bigger than this n, that will imply that our sequence term minus our limit value is smaller than epsilon. So this definition is a bit tricky to understand. So I think two examples will really help us concretely see this definition. So let's examine the sequence 1 over n. And we're going to let that be equal to our an. Clearly, the limit of 1 over n is equal to 0. You should know this from Calc 1. And we're going to let that be equal to our x. Then, in our definition, we said that for all positive distances greater than 0. So we're going to let epsilon of x be equal to 1 over 100. And I'll show by example, I guess, that the n will be equal to 101. So when n is bigger than 101, we'll see that this relationship holds. So terms in the sequence that are equal to or bigger than this are going to be a of 101, a of 102, a of 103, and that's going to be equal to 1 over 101. That's going to be equal to 1 over 102. That's going to be equal to 1 over 103. And we can see here, for each of these, 1 over 101 minus 0 is less than 1 over 100. I'm just going to skip writing the absolute value and the minus 0. They don't really do much to this equation. And then 1 over 103 is less than 1 over 100. And that's going to be true for every term in the sequence after 101. So another little quick example right here. We'll do if we want to look at a different distance, we'll look at 1 over 256. Then clearly our n is going to be equal to 257, because then a, and we're keeping the same a of n in its limit here, and a of 257 is going to be equal to 1 over 257 is less than 1 over 256. What's more important about this is that notice as the small distance changes, we need to ask for a bigger n, right? But one other thing to note is that this n right here is so big that it actually will work for the smaller epsilon value. So we might want to keep that in mind. The idea that we can pick an n so big, it would actually work for 2 of the situations, not just 1. So that's one limit definition that we've covered. But we also know, or we also assume that the limit was equal to b. So that will imply that for all epsilon, or sorry, not b, this should be a y. For all epsilon y greater than 0, there exists an n of y in the element of natural numbers such that when a n minus y is less than, or sorry, no, when n is greater than or equal to n of y, that will imply that a n minus y is less than epsilon y. I don't know what's going on here. Make a lot of mistakes. But we're going to need both of these definitions in order to solve this. So keep both these definitions in the back of your head. So I've written our definitions to the side over there, so we might be able to refer to them. In fact, I'll even give them little numbers. We'll give this one a 1. We'll give this one a 2. You might want that for later. So now I'm going to continue the proof. And the way I want to continue the proof is to do a little bit of a jump. So let's estimate the value of a minus b when n is greater than or equal to the max of n x minus, or comma, n y. And also I wrote a and b. I meant to write x and y. Sorry about that. I wrote in my notes to do a and b, but I changed it to x and y because I didn't want the limit a n, and then I also wanted an a as well. So whoopsies. But anyways, because this isn't an absolute value, we can start off by saying this is going to be at least bigger than 0 or equal to. And the trick here is we're going to want to rewrite this as x minus an plus an. So we're adding and subtracting the same number to an equation, so it won't change the value of the equation. By triangle inequality, we're going to get x minus an plus y minus an. So I'll make sure triangle right there, just so you know. And then, because we asked n to be the max of nx and ny, I'm going to, or not greater than or equal, but strictly greater than, by 1 and 2, so the numbers I have right over here. We know this is going to be epsilon of a plus epsilon of b. Or this is going to be smaller than epsilon of a, epsilon of b. And then I'm going to define epsilon of m, or epsilon x, epsilon of y. Okay, sorry about that. To be the max of epsilon of x, comma, epsilon of y, just so that I can say this will be less than or equal to 2 epsilon m. Just so I have it all down into one variable. It'll make a further step a little easier. To finish this proof, all we have to do is show this final claim to be true. So we want to show that a minus b being less than 2 epsilon max will imply that a is equal to b. Now, doing this directly is a bit trickier. However, we can do a proof via contradiction. So we will assume to the contrary. And that's going to mean we're going to assume that a minus b is less than 2 epsilon m, and a is not equal to b. So because a is not equal to b, that's going to imply that a minus b is not equal to 0. And so the trick is, now that we know that a minus b is not equal to 0, but we also know that a minus b, because it's an absolute value, it's positive, right? So we're going to let epsilon of m to be equal to the absolute value a minus b divided by 2. Or, sorry, divided by 4. And the way we're going to do that is we're going to choose epsilon of a to be equal to a minus b divided by 4, and epsilon of b to be equal to a minus b divided by, I don't know, some huge positive number. Then clearly that'll imply that epsilon of m is equal to a minus b divided by 4, which will then imply that 2 epsilon of m is equal to a minus b divided by 2. That will make the contradiction pretty clear, because we know that a minus b is less than 2 epsilon m, but that's equal to a minus b divided by 2, which is a bit of a question mark. How can a number be smaller than half of itself? And because of that contradiction, we can conclude that a minus b being less than 2 epsilon of m will imply that a is equal to b. And because we showed a is equal to b, we've shown the uniqueness of the limit. So thank you for watching. That concludes the whole proof.